Good morning, everyone. My name is Luis Ferdinand, and I'm from the University of Mercu Buana International class. Today, I'm going to present you Chapter 7 of the Computer Architecture lecture, which are about input and output. This is the final assignment that given by my lecturer as the final test. Chapter 7, Input-Output. External devices. An external device is attached to a computer by a link to an input-output module. The link is used to exchange control, status, and data between the input-output module and the external device. An external device connected to an input-output module is often referred to as a peripheral device, or simply a peripheral. We can broadly classify an external devices into three categories: the human readable, which is suitable for communicating with the computer users. For example, it's the video display terminals, which is VDTS, and printers. The machine readable, suitable for communicating with the equipment, example magnetic disc and tape system, and sensors and actuators, such as are used in robotic applications. Communication, suitable for communicating with remote devices. For example, communication devices allows a computer to exchange data with a remote device, which may be a human-readable device such as a terminals, a machine-readable device, or even another computer. The picture shows the external device's frame. So this is the frame. Example of external devices: keyboard and monitor. The most common means of computer and users interaction is a keyboard and monitors arrangement. The user provides input through a keyboard. The input is then transmitted to the computer and may also be displayed on the monitor. In addition, the monitor displays data provided by the computer. The most commonly used text is the International Reference Alphabet, or IRA. Each character in this code is represented by a unique 7-bit binary code. Those 128 different characters can be represented. Characters are of two types: printable and control. Printable characters are the alphabetic, numeric, and the special character that can be printed on paper or displayed on a screen. Some of the control characters have to do with the controlling, the printing, or displaying of the characters. An example is a carriage return. For keyboard input, when the user depresses a key, this generates an electronic signal that is interpreted by the transducer in the keyboard and translated into the bit pattern of the corresponding IRA code. This bit pattern is then transmitted to the input-output module in the computer. The text can be stored in the same IRA code. On output, the IRA code characters are transmitted to an external devices from the input-output module. The transducer at the devices interpreted this code and sends the requirement electronic signal to the output devices, either to display the indicate characters or perform the requested control functions. The disk drive. A disk drive contains an electronics for exchanging data, control, and status signal with an input-output module, plus the electronics for controlling the disk, read while the read and write mechanism. In fixed head disk, the transducer is capable of converting between the magnetic pattern on a moving disk surface and bits in the device buffer. A moving head disk must also be able to cause the disk arm to move radially in and out across the disk surface. Input-output module. Input-output module have 5 major functions, such as the control and timing, the processor communications, device communication, data buffering, and error detections. These are the major functions or requirements for an input-output module to fall into the control and timing. During any period of time, the processor may communicate with one or more external devices in unpredictable patterns, depending on the program's need for input-output. The internal resources, such as a main memory and the system bus, must be shared among a number of activities including the data input-output. Thus, the information input-output in functions includes a control and timing requirement to coordinate the flow of traffic between the internal resources and the external devices. For example, the control of the transfer of data from the external devices to the processor might involve the following sequence of steps. The first steps, the processor interrogates the input-output module to check the status of the attached devices. And then the second step, the input-output module returns to the device status. And if the device is operational and ready to transmit, the processor requests the transfer of data by means the command of the input-output module. The input-output module obtains a unit of data, for example, 6 to 8 bit, 8 to 16 bit from the external devices. The data are transferred from the input-output module to the processor in the final step. Communication between the processors and external device. There are 4 types, such as command decoding, where the input-output module accepts the command from the processors, typically to send a signal on the control bus. For example, an input-output module for a disk drive might accept the following commands: read sector, write sector, seek the track number, and scan the record ID. The latter 2 commands each include a parameter that is sent on the data bus. The data are exchanged between the processor and an input-output module over the data bus. Status reporting. Because peripherals are so slow, it is important to know that the status of the input-output module. For example, if an input-output module is asked to send a data to the processor to read the data, it may not be ready to do so because it is still working on the previous input-output command. This fact can be reported with a status signal. Common status signals are something like busy and ready. There are many signals report various error conditions also. The addressing recognition. Just as each word of memory has an address, so does each input-output device. Thus, an input-output module must recognize one unique address for each peripheral it controls. Input-output module structure. The module connects to the rest of the computer through a set of system bus lines. The data transferred to and from the module are buffed in one or more data register. One or more status register provide current status information. A status register may also function as a control register to accept detailed control information from the processor. The logic within the module interact with the processor via a set of processors. The logic within the processor uses the control lines to issue commands to the input-output module. Some of the control lines may be used by the input-output module for status signal. Each input-output module has a unique address or a unique set of address if the controls more than one external device. Program input-output. Definition. The program input-output was one of the most simple type of input-output technique for the exchange of data in any types of program of communication between the processors and the external device. With the program input-output, data are exchanged between the processor and the input-output module. There are currently 3 techniques possible for input-output operations, such as program input-output, interrupt-driven input-output, and the direct memory access or DMA. Below is the connection between the 3 technique table. The first one, which is the memory transfer through a processor, we have program input-output and the interrupt-driven. The program input-output, we don't have any interrupts, and the interrupts-driven, we have the interrupts. For the one that direct to the memory transfer, we only have the direct memory access, which also need the interrupts. Command. To execute an input-output related instructions, the processor issues an address specifying the particular input-output module, an external device, and an input-output command. There are 4 types of input-output commands that an input-output module may receive when it is addressed by a processor. First, it's control. Uses the activate a peripheral and then tell it what to do. For example, a magnetic tape unit may be instructed to rewind or move forward one record. These commands are tailored to the particular type of peripheral device. Test. Use of test various status condition associated with an input-output model and its peripherals. The processors will want to know that the peripheral of interest is powered on and available for use. It will also want to know if the most recent input-output operations is completed and if any errors occurred. Read. Cause the input-output model to obtain an item of data from the peripheral and place it in an internal buffer. The processor can be then obtain the data item by requesting that the input-output model place in on the data bus. Write causes the input-output model to take an item of data, bytes or word, from the data bus and subsequently transmit that data to the peripheral. The program input-output flowchart. First, we have the issue reading command to input-output model. After the issues reading, we read the status of input-output model, and then we check the status. If it's not ready, we go back to read the status again until it's ready, and if there is an error, we go to error conditions, and if it's ready, we go to read the word from input-output model and then write the word into the memory, and then we are done. And if there is other thing we want to do, we go back into the first and read the command of the input-output again, and if we are done, we go to next instructions. 2 addressing modes. Memory mapped input-output. With a memory map input-output, there is a single address space for memory, location, and input-output devices that the processor treats the status and data register of input-output as memory locations and uses the same machine register of input-output as memory location and uses the instruction to access both memory and input-output device. So for example, with the 10 address lines, a combined of total of 1024 memory locations and input-output addresses can be supported in any combination. With the memory map input-output, a single read line and a single write line are needed on the bus. Isolated input-output. With isolated input-output, the bus may be equipped with memory, read, and write plus input-output command lines. Now the command line specifies whether the address refers to a memory location or an input-output device. The full range of the address be available for both again with the 10 address line, and the system may now support both 1024 memory location and 1024 addresses. The differences between the two modes. In isolated modes uses the separate memory space, while the memory map input-output uses memory from the main memory. Isolated input-output has limited instructions, which is such as in, out, ins, and outs. And memory map input-output have the instructions which reference to memory can be used. The address for isolated input-output devices are called ports. Memory map input-output devices are treated as memory location on the memory map. Here we have two figures, which is the memory map input-output and the isolated input-output. The figure A shows how the interface for a simple input device such as a terminal keyboard might appear to a program using a memory mapped input-output. Assume that a 10-bit address with a 512-bit memory locations 0 until 511 and up to 512 one's input-output addresses location. Two addresses are dedicated to keyboard input from a particular terminal. Addresses 516 refers to the data status register, which also and addresses 517 refers to the status register, which also functions as a control register for receiving processor's command. The program shown will read 1 byte of the data from the keyboard into an accumulator register in the processor. Note that the processor loops until the data bytes is available. With isolated input-output in the figure B, The input-output port are accessible only by special input-output command, which activate by the input-output command lines on the bus. The advantages of the program input-output is very simple to implement, very little hardware support, and the disadvantages is busy waiting and ties up CPU for a long periods of time with no useful work. Interrupt-driven input-output. Definition. Interrupt-driven input-output is an alternative scheme dealing with input-output. Interrupt input-output is a way of controlling input-output activity whereby a peripheral or terminal that needs to make or receive a data transfer send a signal. This will cause a program interrupt to be set at a time appropriate to a priority level of input-output interrupt for input. The device interrupts the CPU when the new data has arrived and is ready to be retrieved by the system processors. The actual actions to perform depends on whether the device uses input-output ports or memory mapping. For output, the device delivers an interrupt either when it is ready to accept the new data or to acknowledge a successful data transfer. Memory mapped and DMA-capable devices usually generate interrupts to tell the system they are done with the buffer. Simple interrupt processing flowchart. A device drivers initiates an input-output record on behalf of process, and then the device driver signal the input-output controller for the proper device, which initiates the requested input-output. The device signal the input-output controller that is ready to receive input, the output is complete, or that an error has been generated. The CPU receives the interrupt signal of the interrupt requested line and transfer the control over the interrupt handler routine. The interrupt handler determines the cause of the interrupt and performs the necessary processing and executes a return from interrupt instructions. The CPU returns to the execution state prior to the interrupt being signaled. The CPU continues the processing until the cycle begins again. Basic operation of interrupt. First, a CPU issues and read command. Second, input-output modules gets the data from peripheral, which whilst CPU does other work. Input-output module interrupts CPU, the CPU requests data, and input-output module transfer data. The advantages and disadvantages of input-driven input-output, such as the advantages are fast and efficient. The disadvantages can be tricky if using a low-level language, and can be tough to get various pieces to work well together, and usually done by a hardware manufacturer or OS maker such as Microsoft. The design issue. There are two main problems for interrupt input-output, which are there are multiple input-output modules. So how should the processor determine the device that issues the interrupt signal? And how does the processor decide which module to process when multiple interrupts have occurred? So there are four main ways to occur these problems, which are the multiple interrupts lines. As the name suggested, we provide multiple interrupts lines between the processors and the input-output modules. This allows multiple modules to be handled at the same time. However, it is not practical to assign many bus lines and processor pins to the interrupts line. One of the reasons is that there might be more than one input-output module attached to a single line. This defeats the purpose of this technique. The three techniques of the latter are usually used together with this technique to remedy its problems. The software poll. Whenever an interrupt is detected by the processor, it branches into interrupt service routine, which will poll each and every input-output module. to determine the exact interrupting model. The processors raise a poll which could be in the form of a command line. Consequently, the address of the respective input-output model which is interacted by the poll will be placed on the address line. The module will respond positively if it's the responsible for the setting the interrupt. On the other hand, every input-output module has an addressable status register. This register can be read by the processors to determine the interrupt model. After that, the processor then branches to a specified device service routine. The downside of this technique is that it is time-consuming. The daisy chain. This is actually hardware poll. The interrupt acknowledge line is a daisy chain to all the modules. Whenever there is an interrupt, the processor send out an interrupt acknowledgement which will propagate throughout the series of input-output modules. This process will continue until it reaches a requesting module. The data lines, the word is known as vector. This vector can either be addressed to of the modules or a specified directs the modules to its specified device service routine based on its vectors. This technique is also known as the vectors interrupt. It completely removes the needs for interrupts-driven routine. The bus abbreviations. The last method, which also utilizes vector interrupts, is bus abbreviations. This method involves the input-output module gaining control over the bus before requesting for the interrupt. This is limited to only one module at a time. The processor sends an acknowledged signal whenever it detects an interrupt. The requesting module then places its vector on the data lines. These four methods have their own ways of assigning priorities. The first one, multiple interrupts line. The processor picks the interrupt with the highest priority. The second one, software poll. Software poll determined by order in which the modules are in poll. The daisy chain. Daisy chain priority is determined by the order in which the modules are polled also. The bus abbreviations employs a priority of a scheme. The interrupt structure example. This is the interrupt control and external interrupt are better. Main purpose is managing interrupts, especially acknowledgement, our INTA line. They connect to the external device and then into Intel X03, X6, allowing the handling of a variety of devices and priority structures. A single egg to C59A can connect to 8 input-output module. Can be arranged in cascade arrangement for 264 modules, and it has 3 modes. First one is fully nested, interrupts requested ordered based on priority. The second one is rotating. Some applications have an equal priority, thus a particular device has lowest priority in the group after being serviced. The third one is special marks, which are the processors can inhibit interrupts from some devices. Direct memory access or DMA. Definition. Direct memory access is a technique for transferring data within main memory and external devices without passing it through the CPU. DMA is a way to improve processors' activity and input-output transfer rate by taking over the job of transferring data from the processor and letting the processor to do other tasks. This technique overcomes the drawbacks of the two input-output technique, which are commands, which are the time-consuming process when ensuing command for data transfer, and tie up the processor in the data transfer while the data processing is neglected. It is more efficient to use DMA method when large volume of data has to be transferred. For DMA to be implemented, processor has to share its system bus with the DMA module. Therefore, the DMA module must use the bus when the processor does not need it, or it must force the processor to suspend operation temporarily. The latter technique is more common to be used and is referred to as cyclic stealing. DMA interrupt breakpoint during an instruction cycle, we can see as this picture. Basic operation of DMA. When the processor wishes to read or send a block of data, it issued a command through the DMA module by sending some information to the DMA module. The information including the read and write command, which is sending through read and write control lines, the number of words to be read and written, communication on the data lines and stored in the data count register, the starting location in memory to read from or to write to, it is communicated on the data lines and stored in the address register, the address of the input-output devices involved, which is communicated on the data input lines. After the information are sent, the processor continues with other work. The DMA module then transfers the entire block of data directly to or from memory without going through the processors. When the transfer is completed, the DMA module sends an interrupt signal to the processor to inform that it has finished using the system bus. DMA mechanism and configurations. DMA mechanism can be configured in a variety of ways, which are: the first one is single detached DMA, a single bus detached DMA, all modules shared in the same system of bus. The DMA module is acting as a surrogate processors, which uses program input-output to exchange data between memory and an input-output module through a DMA module. This configuration is inexpensive, but it is inefficient. This is because each transfer of words consumes 2 bus cycles. Single bus detached DMA. In this configuration, there is a path between 2 of the DMA module and 1 or more input-output module that does not include the system bus. The DMA logic can be a part of an input-output module or a separated module that controls 1 or more input-output module. Therefore, the number of required bus cycles can be cut substantially. The system bus that the DMA module shares with the processors and memory is used by the DMA module only to exchange the data between the DMA and input-output module takes place of the system bus. Input-output bus. In these configurations, the concept further improves from the previous configurations, which is single bus integrated DMA. The input-output modules are connected to the DMA module using an input-output bus. This can reduce the number of input-output interfaces for an easily expandable configuration. The system bus that the DMA module shares with the processors and memory is used by the DMA module only to exchange data with the memory. The exchange of data between the DMA and input-output module take place in the system bus. The advantages and disadvantages of the DMA. Advantages: allows the peripheral device to read from and write to memory without going through the CPU. Allows for faster processing since the processor can be working on something else while the peripheral can populating memory. The disadvantages is requires a DMA controller to carry out the operation, which is increase the cost of the system and cache coherence problems. Direct cache access. Direct cache access approach implemented by Intel. Direct cache access (DCA) allows a capable input-output device, such as a network controller, to place data directly to CPU cache, reducing the cache misses and improving application response time. The Xeon multi-core processors. The Xeon E-VIVE 2600/4600. Intel Xeon is Intel's high-end, high-performance processor family used in servers, high-performance workstation, and supercomputers. The E52600/4600 can be configured with up to 8 cores on a single chip. Each core has dedicated to level 1 and level 2 cache. There is a shared level 3 cache of up to 20 MB. The level 3 cache is divided into slices, one associated with each core, although each core can address the entire cache. The bidirectional high-speed ring interconnects link cores, last level cache, PCIe, and Integrated Memory Control or IMC. In essence, the ring operates as follows. Each component that attaches to the bidirectional ring, which is QPI, PCIe, level 3 cache, and level 2 cache, is considered a ring agent and implemented ring agent logic. The ring agents cooperate via a distributed protocol to request and allocate access to the ring in the form of time slots. When an agent has data to send, it chooses the ring to direction that resolve in the shortest path to the destination and transmit when scheduling slot is available. The ring architecture provides good performance and scales well for multiple cores up to a point. For a system with a greater number of cores, multiple rings are used, with each ring supporting some of the core. This is the Xeon E52600/4600 chip architecture. You can see here at the picture. The cache-related performance issue. When large volume of protocol traffic are processed, two factors in this scenario degrade performance. First, the core consumes valuable clock cycle in copying data between system and application buffer. Second, because memory speed have not kept up with the CPU speed, the core loses time waiting on the memory reads and writes. In this traditional way of processing protocol traffic, the cache does not help because the data and protocol's headers are constantly changing, and thus the cache must constantly be updated. Cache-related performance issue. To clarify the performance issue, we need to explain first the benefit of the DCA as a way of improving performance. Let us first look at the processing of the protocol traffic in more detail in incoming traffic. In general terms, the following step occurs. The packet arrives. The NIC receives an incoming Ethernet packet. The NIC processes and strips off the Ethernet control informations. This includes doing an error detection calculation. The remaining TCP/IP package is then transferred to a system DMA modules, which generally is part of the NIC. The NIC also creates a package descriptor with information about the package, such as its buffer location in memory. DMA. The DMA module transfers data, including the packet descriptor, to main memory. It must also invalidate the corresponding cache line if any. NIC interrupt host. After a number of packets have been transferred, the NIC issues an interrupts to the host processors. Retrieve a descriptors and headers. The core process the interrupts invoking an interrupts handling procedures, which reads the descriptors and headers of the received packets. Cache miss occur. Because this is new data coming in, the cache lines corresponding to the system buffer containing the new data are invalidated. Thus, the core must stall to read the data from the main memory into cache and then the core register. Header is processed. The protocol software executes on the core, analyzes the content of the TCP and IP headers. This will likely include accessing a transport control block or TCB, which contains information related to TCP. TCB access may not trigger the cache miss, necessitating a main memory access. Payload transfer. The data portion of the package is transferred from the system buffer to the appropriate application buffer. Okay. A similar sequence of steps occur for outgoing packet traffic, but there are some differences that affect how the cache is managed. For outgoing traffic, the following steps occur. First, the packet transfer requested. When an application has a block of data transfer to a remote system, it places the data in an application's buffer and alerts the OS with some type of system call. Package created. The OS invokes to a TCP/IP process to create a TCP/IP package for transmission. The TCP/IP process accesses the TCP, which may involve a cache miss, and then creates the appropriate headers. It also reads the data from the application buffer, and then places the complete package, headers plus data, in a system buffer. Note that the data that is written into the system buffer also exists in the cache. The TCP/IP process also creates a package descriptor that is placed in a memory shared with the DMA model. Output operation involved. This uses a device driver program to signal the DMA model that output is ready for the NIC. DMA transfer. The DMA model reads the package descriptor, then the DMA transfer is performed from main memory or the last level cache to the NIC. Note that the DMA transfer invalidates the cache line in cache even in the case of read by the DMA model. If the line is modified, this causes the write back. The core does not do the invalidates. The invalidates happen when the DMA modules reads the data. NIC signal completion. After the transfer is complete, the NIC signal the driven to the core that originated sent to signal. Drivers free buffer. Once the driver receives a completion notice, it frees up the buffer. For reuse, the core must also invalidate the cache line containing the buffer data. As can be seen, the network input-output involves a number of accessing to cache and main memory and the movement of data between an application's buffer and a system buffer. The heavily involvement of main memory becomes a bottleneck, as both core and network performance outstrip gains in memory access times. Direct cache access strategies. Several strategies have been proposed for making more efficient use in cache for input-output. With the general terms direct cache access applied to all these strategies, the simplest strategies is one of what implemented as a prototype of a number of Intel Xeon processor between 2006 and 2010, which is in KUMA07 and INTE08. This form of DCA applies to incoming network traffic. The DCA function in the memory control send a prefetch hint to the core as soon as the data available in the system memory. This enables the core to prefetch the data package from the system buffer, thus avoiding cache misses and the associated waste of core cycles. While the simpler form of DCA does provide some improvement, much more substantial gains can be realized by avoiding the system buffer in main memory altogether. For the specific function of protocol processing, note that the package and package descriptor information are accessed only once in the system buffer and by the core. For incoming package, the core reads the data from the buffer and transfer the package payload to an application buffer. It has no need to access that data in the system buffer again. Similarity to for the outgoing package, once the core has placed the data in the system buffer, it has no need to access that data again. Suppose, therefore, that the input-output system were equipped not only with the capability of directing accessing main memory, both for input and output operations, then it would be possible to use the last level cache instead of main memory to buffer the package and descriptors for incoming and outgoing package. This last approach, which is true DCA, was proposed in HUGG05. It has also been described as cache injections, LEON06. A version of this more complete form of DCA is implemented in Intel's Xeon processor's line, referred to as Direct Data Input-Output or DDIO of INTE12. Direct Data Input-Output. Intel Direct Data Input-Output DDIO is implemented on all of the Xeon family of the processors. Its operation is best explained with a side-by-side comparison to transfer with or without the DDIO. Before discussing of the processing and of an incoming package using DDIO, we need to introduce a new technique for the following discussion. There are issues relating the cache concurrency that arise in a multi-core or multi-core environment. This will discuss in chapter 17, but the details need not to be concerned us here. Recall that there are two techniques for dealing with an update to a cache line, which is write-through. All write operations are made main memory as well as to cache, ensuring that main memory is always valid. Any other core cache modules can monitor traffic to main memory to maintain consistency within its own local cache. Write-back updates are made only in the cache. When an update occurs, a dirty bit associated with the line is set. Then, when a block is replaced, it is written back to main memory if and only if the dirty bit is set. DDIO uses the write-back strategy in L3 cache. A cache write operation may encounter a cache miss, which dealt by one of two strategies, such as write allocate. The required line is loaded into the cache from main memory. Then the line in the cache is updated by the write operation. The scheme is typically used with the write-back method. The non-write allocate. The block is modified directly into the main memory. No change is made to the cache. This scheme is typically used with the write-through method. The DDIO strategy for inbound transfer is initiated by the NIC. If there is a cache hit, the cache line is updated, but not main memory. This is simply the write-back strategy for the cache hit. The Intel literature refers this to a write update. If there is a cache miss, the write operation occurs to a line in the cache that will not be written back to main memory. Subsequent write is updated to the cache line, again with no reference to main memory or no future actions that writes this data to main memory. The Intel documentation INTE12 refers to this as a write allocate, which unfortunately is not the same meaning for the terms in general cache literatures. The DDIO strategy is effective for a network protocol application because the incoming data need not to be retained for future use. The protocol application is going to write the data to an application buffer, and there is no need temporary storage store it in a system buffer. Now we're going to compare the DMA and DDIO. First, we look at the case of the package arriving at the NIC from the package. The figure A shows that the step involved for a DMA operation. The NIC initiates a memory write, then the NIC invalidates the cache line corresponding to the system buffer. Next, the DMA operation is performed, thus posting the package directly into main memory, and finally, after the appropriate core receive a DMA interrupt signal, the core can read the package data from the memory through the cache. You can see here. Okay, in figure B shows the operation for DDI input. The NIC initiates memory writes in the first step, and then the second step, the NIC invalidates the cache lines corresponding to the system buffer and deposit the incoming data in the cache. In the third one, we finally, after the appropriate core receive a DCA interrupt signal, the core can read the package data from the cache. In the figure C shows the steps involve a DMA operation for outbound package transmission. The TCP/IP protocol handler the executing of the core reads data in from an application buffer and writes it out to a system buffer. This data access operation result in a cache misses. Figure C shows the step involved for DMA operation for outbound package transmission. The TCP/IP protocol's handler executing on the core reads the data it from an application buffer and writes it out to a system buffer. This data access operating result in cache misses and cause the data to be read from memory into the L3 cache. When the NIC receives a notification from starting transmit operation, it reads the data from level 3 cache. Level 3 cache here, last level cache, and then the transmitted. The cache access by the NIC cause the the data to be affected from the memory cache and written back to main memory. The last figure, figure D, shows the steps involved for DDO operation for package transmission, which is output. The TCP/IP protocol first handler that creates the package to be transmitted and store it in allocate space in last level cache, but not in the main memory, only in here. And then the read operation initiated by the NIC is satisfied by the data from the cache without causing affection to main memory. It should be clear from the side-by-side comparison that the DDO is more efficient than the DMA for both incoming and outgoing package, and is therefore better able to keep up with the high package traffic rate. Input-output channels and processors. Evolution of input-output. The evolution step can be summarized as follows. The CPU directly controls the peripheral device. This seen in a simple microprocessor's control devices. The control of input-output is added. The CPU uses program input-output without interrupts with the step, and the CPU becomes somewhat divorced from the specified details of the external device's interface. The same configuration as in step 2 is used, but now interrupts are employed. The CPU need not spend time waiting for an input-output operations to be performed, thus increasing efficiency. The input-output model is given direct access to memory via DMA. It can now move a block of data or from a memory without involving the CPU, except the beginning and the end of the transfer. 5 step, the input-output model is enhanced to become a processor in its own right, with a specialized instruction set tailored for input-output. The CPU directs the input-output processors to execute an input-output program in memory. The input-output processors fetch and execute this instruction without CPU intervention. This allows the CPU to specify a sequence of input-output activities and to be interrupted only when the entire sequence has been performed. The input-output module has a local memory of its own and it's, in fact, a computer of its own right. With this architecture, a large set of input-output devices can be controlled with minimal CPU involvement. A common use of such architecture has been control communication with interactive terminals. The input-output processor takes care of most of the tasks involved in controlling the terminals. Characteristic of input-output channels. The input-output channel represents an extension of DMA concept. An input-output channel has the ability to execute input-output instructions which give it complete control over operations. The two types of input-output channels are common, such as selector channels and multiplexer channels. Selector channels and multiplexer channels. Selector channels control multiple high-speed devices and at any one time is dedicated to transfer of data with one of those devices. Thus, the input-output channels select the one device and affects the data transfer. Each device or small set of device is handled by a controller or input-output model that is much like the input-output models we have been discussing. Thus, the input-output channels serve in the place of the CPU controlling these input-output controllers. This is the scheme of the selector channel. A multiplexer channel can handle an input-output of multiple devices at the same time. For low-speed devices, a byte multiplexer accepts or transmits character as fast as possible to multiple devices. Here are the multiplexer scheme. External interconnection standard. Thunderbolt and InfiniBand. Thunderbolt, the most recent and one of the fastest peripheral connection technology to become available for general purpose, is a Thunderbolt. Developed by Intel with collaboration from Apple, one Thunderbolt cable can manage the work previously required of multiple cables. The technology combines data, video, audio, and power into a single high-speed connection for a peripheral such as hard drives, RAID, redundant array of independent disk arrays, video captures boxes, and network interface. It provides up to 10 gigabytes per second throughout in each direction, up to 10 watts of power connected peripherals. InfiniBand. InfiniBand is an input-output significant aimed at the high-end server market. The first version of the specification was released in early 2001 and has attracted numerous vendors. For example, IBM Z Enterprise series of mainframes has relied heavily on InfiniBand for a number of years. The standard describes an architectures and specifications for data flow among processors and intelligent input-output device. InfiniBand has become a popular interface for storage area, networking, and other language storage configuration. In a sense, InfiniBand enables servers, remote storage, and other network devices to be attached in the central fabric of switch and link. The switch-based architecture can connect up to 64,000 servers, storage system, and networking device. Universal Serial Bus, or USB. USB is widely used for peripheral connections. It is the default interface for slow-speed devices such as a keyboard and a pointing devices, but it's also commonly used for high-speed input-output, including printers, disk drives, and network adapters. USB has grown through multiple generations. The first version, USB 1.0, defined a low-speed data rate of 1.5 megabyte per second and full speed of 12 megabyte per second. The USB 2.0 provides a data rate of 480 megabytes per second. USB 3.0 includes a new higher speed bus called SuperSpeed in a parallel with the USB 2.0 bus. The signaling speed for SuperSpeed is 5 GB per second, but due to signaling overhead, the usage data rate is up to 4 GB per second. The most recent specification is USB 3.1, which includes the faster transfer mode called SuperSpeed Plus. This transfer mode achieves a signaling rate to 10 GB per second and a theoretical usable data rate of 9.7 GB per second. USB system is controlled by a root host control which attached to devices to create a local network with a hierarchical tree topology. The Wi-Fi. Wi-Fi is the predominant wireless internet access technology used in homes, office, and public spaces. Wi-Fi is in the home now connects to computers, tablets, smartphones, and a host of electronic devices such as video camera, TVs, and thermostat. Wi-Fi in the enterprise has become essential means of enhancing workers' productivity and network effectiveness, and a public Wi-Fi hotspot have expanded dramatically to provide free internet access in most public places. As technology of Ethernet's wireless transmission techniques and wireless protocol design has evolved, the IEEE 802.11 committee has been able to introduce standards for new version of Wi-Fi at ever higher speeds. Once the standard is issued, industry quickly developed the develop the products. Here is brief chronology, starting with the original standard, which was simply called IEEE X011, and showing the maximum data rate for each version. The 802.11.11, which is created in 1997, only have the speed of 2 megabytes per second. 802.11a, which is created in 1999, have the speed of 54 megabytes per second. 802.11b, which is also created in 1999, have the speed of 11 megabytes per second. 802.11n, which is also created in 1999, have the speed of 600 megabytes per second. 802.11g, which is created in 2003, have the speed of 54 megabytes per second. 802.11ad, which is created in 2012, have the speed of 6.76 gigabytes per second, which is have the billion bits per second. 802.11ac, which is created in 2004, have the speed of 3.2 gigabytes per second. Other Ethernet interconnections are the Firewire Serial Bus, the SCSI, which is Small Computer System Interface, the PCI Express, SATA, and Ethernet. The IBM ZE Enterprise AC12 input-output structure. The system is based on the use of the ZE-C12 processor chip, which is a 5.5 GHz, 5.5 GHz multi-core chip with 6 cores, and the ZE-C12 architectures can have maximum of 101 processors chips for a total of 606 cores. These are the channel structures, which we can see have less than 60 partition per system and less than 1024 partition per system. Well, of the 96 cores processors, up to 4 of these can be dedicated for input-output use, creating 4-channel subsystem CSS. Each CSS is made up of the following element. First one is SAP, which is System Assist Processors. It's a core processors configured for input-output operation. Its role is to offload input-output operation and make channels the input-output operations queries. It relieves the other processors of all input-output tasks, allowing them to be dedicated to application logic. Hardware System Area, or HSA, is a reserved part of the system memory containing the input-output configurations. It is used by the SAPs. A fixed amount of 32 gigabytes is reserved, which is not part of the customer process memory. This provides for a greater configuration flexibility and higher availability for eliminating pre-planned outages. Logical partitions. A logical partitions is a form of virtual machines which is in sense a logical processor defined at the operating system level 3. Each CSS supported up to 16 logical partitions. Subchannels appears for a program as a logical device and contains the information requires perform and operations. One subchannel exists for each input-output device. The information required for addressable by the CSS. A subchannel is used by the channel's subsystem code running on a partition to pass an input-output request to the channel subsystem. A subchannel is assigned for each device defined to a logical partitions up to 196,000 subchannels supported per CSS. The channel path. A channel path is a single interface between the channel subsystem and one of more control units via a channel commands, and the data are sent across a channel's path to perform an input-output request. Each CSS can have up to 256 channel paths. Channels. Channels are small processors that communicate with an input-output control unit, or CUS. They manage the data transfer between memory and external devices. The IBM Zenterprise EC12 input-output structure. The physical layout. The weight we have 2,430 kilogram. The width we have 1.568 meter. The depth we have 1.69 meter, and the height we have 2.015 meter. As you can see here, it has the internal batteries that is optional at the top, and then they have the power supplies below it, and the support elements below the power supplies, and the PCI input-output drawer. It has flexible services processor (FSP) controls card, the processor's books with memory HCA and PCIe fan-out cards, the InfiniBands and the PCIe interconnects, the input-output cage carried forward, and N+1 water cooling units. This is the front views, and this is the structure in the drawing. I think that's all I can explain to end these sections. Thank you for listening until the end. I hope you can earn any good informations for learning. And one more time, thank you for listening until the end.